Going to go ahead and move on to our last presentation today from the group titled Wabtec Gear Removal Process, advised by Dr. Ulrich. Are you guys present and ready to go?
Yes, Dr. Barty.
Perfect. So the first person presenting, please activate your video and be sure everybody to introduce yourselves as you're passing from one person to the next. Go ahead.
All right, thank you, Dr. Barty. Good evening, all. Thank you for joining us as we present our Wabtec gear removal project. My name is Nick Fox, and I'm the team leader for our capstone design team. We've done a lot over the semester, so without further ado, let's get started. So just before we get into the project, a little bit about our project sponsor. Wabtec Corporation was formed when Westinghouse Air Brake Company merged with Motive Power Industries Corporation in 1999. Wabtec was brought into Grove City by their merger with GE Transportation in May 2018, which was completed early 2019. Wabtec does all sorts of train manufacturing. They do freight cars, they do people movers, they do locomotives as well. And there's two facilities actually in town. The one you see a lot is the one on the east side by Walmart. That's the manufacturing plant that they have in town. And then there's actually one north of the college you see in the bottom right corner. That's their remanufacturing plant, and that's where our apparatus is going to be implemented. Our project objective starts with Wabtec's Evo locomotive engine. When an old or broken locomotive engine comes into the remanufacturing plant, it's disassembled and cleaned. The crankshaft of the Evo engine has a gear, as you can see there in the right picture, and it drives the upper half of the engine. Think the cams and the timing mechanisms of the engine you see in the bottom left corner. That gear can be salvaged and reused, saving Wabtec money. The gear is press fit onto the shaft, and it has some special characteristics that we'll get into later, but just know that it makes it extremely difficult to remove that gear from the crankshaft. So this is where we come in. A prototype apparatus is to be designed, manufactured, and delivered to Wabtec. Wabtec gave us certain design requirements to meet. The two most important ones are the successful recovery of 80% of the gears and a maximum of 30 minutes touch time for removal. Those are the most important requirements, the theta meaning they are critical to quality. They also gave us 4 other we call soft requirements. One is the ability and versatility to use on broken crankshafts. Crankshafts come in all different conditions, so just that versatility to use on whatever they may receive in the remanufacturing plant. The ability to remove the gear without damaging the crank. They wanted to avoid the need for a larger hydraulic pump because they already have a hydraulic pump on their shop floor. They wanted us to tailor our design to said pump, and they also wanted us to keep a tool replacement cost of under $10,000. So here's just a glimpse of our solution, and we'll break it down for you guys as we go. The large gray piece is the Evo crankshaft section view of it. The red is the gear that we're trying to salvage. And as you can see, the lime green is a hydraulic port, and that's how they can apply hydraulic pressure to the gear, and it actually floats, they call it. And it can move axially on the shaft and rotate 360 degrees. That allows them to, whenever they install it, to line it up perfectly because, like I said before, it drives some really important stuff on their engine. The orange piece is the collar. This is everything from now on will be stuff that we designed. The collar shares that same hydraulic port characteristic, and it seals up to the gear face to keep that hydraulic pressure underneath the gear, in between the gear and the crankshaft. The blue piece is the clamp assembly, and that is designed to keep all that hydraulic pressure in. There's a lot of pressures you'll learn later, so it's very important that that was a robust design of ours. And once hydraulic pressure is applied to the gear and collar, it slides onto the sleeve, which is the yellow piece that you see there. And I'll pass it off to Sam Bronny to tell you more about the sleeve.
All right, so a lot of my responsibility on this project had to do with design of the sleeve, which is the yellow component you see there. The purpose of the sleeve in the design was to minimize the cross-sectional area associated with the hydraulic fluid by reducing, and therefore reduce the axial forces in the system. So you can imagine if we took the sleeve out of the design and you just had the orange collar there, extending all the way down to the smaller diameter of the shaft instead of up to the sleeve, you would have hydraulic fluid filling the cavity where the sleeve now sits. This would create an axial force produced by the 10,000 pounds per square inch of hydraulic fluid, and that would create an axial force on the entire apparatus of about 200,000 pounds. This force would be much too large for our design to handle and would cause very, very high stresses. So to combat that, we put the sleeve in the design. You can see the blue O-ring on the left edge of the yellow sleeve there seals the hydraulic fluid so that it only goes on the top surface of the sleeve, therefore drastically reducing the axial cross-sectional area on the sleeve. Now, despite this reduction of axial force, the sleeve still undergoes a lot of stress, and to handle that, we selected a 4140 tool steel hardened to have a yield strength of about 850 megapascals at a minimum. Now, to illustrate the stresses in the sleeve, we analyzed them with finite element analysis. You can see on the plot to the left, the von Mises stress in the sleeve comes out to about a maximum of 550 megapascals, which is below the yield point. You may also notice that the highest stress is there's a line on the inner diameter of the sleeve, which represents the hydraulic relief grooves in the sleeve. These hydraulic relief grooves are a safety feature. If our O-ring fails, hydraulic fluid will merely leak through the inner diameter of the sleeve instead of creating a large axial force. Furthermore, this leakage will allow the operator to see visibly that there's been a failure in the O-ring so that they can do the proper maintenance on the tool. The plot on the right shows the displacement of the sleeve under hydraulic pressure. And you'll notice that it comes in quite a bit, 0.5 millimeter radially under the high pressure. And we had to account for this in our clearance with the shaft. So this is a little bit about our method for designing the sleeve. What you'll notice here is that there's really not very much geometric variability built into this design. So the main thing here was the outside diameter of the orange collar there. So the collar and the sleeve are press fit, and they're designed so that the pressure of the press fit with the gear and the collar matches the press fit with the collar and the sleeve. So you have the gear and the crankshaft and the collar and the sleeve with the same pressure so that they can float off simultaneously while attached to the same pump. If the collar ID or if the collar OD was too large, this would decrease our tolerances by increasing the stiffness and decreasing the displacements. And if we made the collar too thin, that would increase our stress significantly. So we sort of picked a happy medium, and that's how we designed the fit between the sleeve and the collar. I'm now going to pass it off to Joe Grindy to talk about the collar.
I'm Joe Grundy, and I'll be talking about the collar. As Sam mentioned, the collar will be hydraulically floated onto the sleeve by supplying pressurized hydraulic fluid into the hydraulic inlet and groove, which are both shown in green. The collar has the same hydraulic inlet and groove as the gear, so that the same pump setup can be used for both. After, the collar will be floated the entire length of the sleeve and will be sealed to the face of the gear with an O-ring, shown in the bottom left photo. In terms of material, the collar will have very high stresses, similar to the sleeve, so it will be made out of the same 4140 steel that the sleeve was made out of, again with an estimated yield strength of 800 megapascals. When setting up analysis for the collar, a 10,000 psi pressure load was applied to the inner diameter, which simulates the pressure of the hydraulic fluid. In addition, the total axial load caused by the clamp bolts is 60,000 pounds, which equates to around 10,000 pounds per bolt surface region. The surface region size has the diameter of the end of an M18 bolt, which is what is being used for the clamps. So this is our finite element analysis summary of the collar. The highest stress occurs in the hydraulic inlet hole at around 691 megapascals, which is about 160 lower than the allowable 850 before the collar begins to yield. All other stresses in the critical areas fall well below the allowable stress. Also shown here is the axial bolt displacement and the radial displacement. These values are acceptable and small enough so that they don't raise concerns for functionality. So these are the stress plots for the collar. On the left, you'll see the hydraulic inlet. The red shows the highest stress occurs, which is around 691 megapascals. And to the right is the second highest stress in critical areas, which is the M8 hole, which is used for lifting. And this plot shows the stress on the inner diameter, which is the lowest stress in terms of critical areas at around 330 megapascals. And here are the displacement plots for the collar. The axial bolt displacement plot is shown to the left, and visually can be seen by the 6 circular surface regions on the plot. And also the radial displacement plot is shown to the right, showing displacement in the vertical direction. Now Kyle will take over and talk about the backing plate.
Hello, I'm Kyle Smith, and I'll be talking about the design and analysis of the backing plate. The purpose of the backing plate is to hold the sleeve in place, as well as maintain the sleeve face seal. For the sleeve face seal to maintain proper compression, the backing plate must not have an axial deflection that is greater than 0.26 millimeters. The backing plate is secured to the assembly by the M42x3 bolt. These components can be seen in the figures at the bottom of the screen. The backing plate is made from A514 tool steel that has a yield strength of 700 megapascals. A force of 58,700 pounds is applied to the backing plate during the removal process. And this force is the result of the hydraulic pressure acting on those sleeve surfaces that are above the seal. Next slide. The final backing plate design features a clearance hole at the center for the M42 bolt. It also is 50.8 millimeters thick and is tapered down to 21.4 millimeters at the sleeve contact surface. The design has 6 tabs that are equally spaced 60 degrees around the edge of the plate. And these tabs all have an M8 hole that allows for the installation of eye bolts. The eye bolts give Wabtec the option of using a crane during the attachment process to the assembly, if that is desired. And the backing plate also has a 4 millimeter boss for stabilization and alignment into the sleeve, and that can be seen at the bottom right figure there. Next slide, please. So due to the symmetry of the backing plate design, a cyclic symmetric constraint was used in the finite element analysis. This constraint helped simplify the analysis and improved its accuracy as well as speed. The figure to the left shows the axial displacement of the backing plate resulting from the 58,700 pound load. The max displacement at this sleeve contact surface is 0.16 millimeters. This result is less than the maximum allowable deflection of 0.26 millimeters, and this result gives the team confidence that we'll be able to maintain that sleeve seal. The stress analysis of the backing plate originally resulted in a stress concentration, stress singularity at the washer and M42 bolt contact surface. And to gather more accurate results, a reversed loads analysis was created. And this analysis is seen in the figure to the right. The stress in this area of concern did not exceed 355 megapascals, which is significantly lower than the yield strength of the material used in the backing plate. Now I'm going to pass it off to Jake to talk about the clamps.
Hi, I'm Jake Wright, and I've done a lot of work with clamps this year. So one of the main challenges we faced with using the collar to maintain float pressure on the gear was preventing the collar and the gear from being forced apart when hydraulic pressure is applied. To handle this issue, the team decided to develop a clamp system that will hold the collar and the gear together. We determined that the best clamps needed to be capable of providing sufficient clamping force. They needed to be lightweight so that they could be handled easily, and they needed to be quick and easy to use to minimize error and touch time. The clamps are made from a 4140 steel and are shaped to slide over both the gear and the collar easily, as seen in that bottom figure. An M18 screw closes the clearance and keeps the gear and the collar intact. We found that the hydraulic fluid exerts a total of approximately 58,520 pounds of separating force between the collar and the gear. Our use of 6 evenly distributed clamps results in about 9,700 pounds of clamp. Performing finite element analysis on the clamps, we saw that the final clamp geometry saw a maximum stress of only about 245 megapascals. This was also seen in sharp modeled corners that don't actually exist when the part is manufactured. So the actual maximum stress may be slightly smaller. Regardless, the stress is less than half of the ultimate strength of 4140 steel, which means that the clamps will stand up to both the initial loading and any fatigue stresses. We saw, looking at that second figure, the maximum displacement that the clamps will allow between the gear and the collar faces is approximately 0.294 millimeters, which is acceptable to maintain a proper seal with our chosen O-rings. And the final clamps weigh only 6 to 7 pounds apiece, which can be easily lifted and handled. Next slide, please. So in order to further improve the convenience of the clamps, a handle system was implemented, and this was made by simply bolting 2 clamps to 3 bent tube handles, and you can see the entire assembly in the bottom figure on this slide. The top handle has 2 screws protruding from the bottom, looking at this top figure, and the side handles have a tab which will fit over those screws on the top handle. These handles allow operators to mount the top 2 clamps and then proceed to hang the 2 side handles from the top and swing the clamps into place. This feature allows for faster assembly time as well as guarantees an even 60-degree spacing between the clamps, and also gives the operator something to hold on to when guiding the gear off of the shaft. At this point, I will hand things off to Matt to discuss the hydraulic setup.
Thank you, Jake. I will be talking about the hose assembly as well as the removal process. So after designing the collar and keeping in mind that we wanted to use the same pump that Wabtec provided to us, we needed a design that would handle both the gear and the collar. So we came up with this design and sent it out, and we heard back from a company who spec'd this for us. So what we wanted was a valve on each side so we could independently or simultaneously float the gear and the collar. And we also wanted 6 feet of hose on each side just for easy use. So the first step of the removal procedure is to float the gear using the hydraulic pump. And you're going to slide the gear axially until pressure is lost. You're then going to slide the sleeve and the collar combination onto the smaller end of the crankshaft, and you're going to ensure that the O-rings, which are seen in blue, are fitted properly. You're then going to attach the backing plate using the M42 bolt and tighten. You're then going to apply the other side of the pump to the collar and float the collar to the gear. You're then going to install the clamps. And then you're going to float both. You're going to apply hydraulic pressure to the collar and the gear. You're then going to slide the collar and the gear combination down to the end of the crankshaft, noticing that there is clearance between the clamp handles and the backing plate. You're then going to depressurize the collar and the gear. You're going to remove the backing plate. And this next step is up to Wabtec. It depends on what is ever easiest for them. The first option is to carry the whole assembly away via crane and put it on a workstation such as a moving cart, or you could remove the clamps and float and take away the sleeve and the collar and allow the gear to slide onto the smaller portion of the crankshaft. And now I will hand it off to Alex to talk about the testing plan and finances.
All right, so hello everyone, my name is Alex Traxel, and like Matt said, I'll be talking about our testing plan. Our first, unfortunately, we weren't actually able to conduct our testing plan due to the coronavirus pandemic that affected our end of our semester plans. However, we still had a plan that we were going to put into place if we were able to actually be on campus and test our apparatus. So the first test we're going to conduct was a fit-up test, which included taking all of our manufactured and purchased components and install them onto a portion of a shaft that Wabtec provided us that can be seen in the bottom portion of the slide. With this test, our goal is to make sure that all of our parts fit together as we intended, and also to make sure all of our sealing surfaces interface correctly. And once we verified that we passed our fit-up test, we were then actually going to apply float pressure to the apparatus inside of Hoyt and try to successfully remove a gear. Once this gear is removed, we were then going to inspect both the gear and the apparatus for wear to make sure our device withstanded the forces of removing the gear, as well as if in the situation we weren't able to remove the gear, this was going to be our time to troubleshoot it and try to find solutions before taking the project to Wabtec. So once we were confident, we were then going to take the apparatus to Wabtec and try to remove 10 or more gears at their facility in Grove City. Our goal of removing 10 gears was to see if we can meet the 80% success rate that we established with Wabtec as a good passing criteria for our project. Additionally, while removing those gears, we wanted to time how long it took us to assemble the apparatus, conduct the whole process, and remove the gear to see if we're going to meet our average 30-minute touch time goal. That was additionally our critical to quality requirement for this project. So next, we're going to talk about some finances of our project. So thankfully, due to Wabtec sponsoring this project, we had a generous $10,000 budget. And of that $10,000 budget, we had $8,000 that was controlled by the team to purchase components, as well as to fund manufacturing and outsource components if we needed them produced by outside vendors. Additionally, the other $2,000 was controlled by Wabtec, and that was so that they can purchase components for us, such as gears, and fund the providing us the shaft, as well as any other tooling we may need for testing. So overall, we only spent $4,371 of that team-controlled $8,000, which was only 54.6% of our team-controlled budget. However, it is important to note that those spent funds do not include any student labor or any expenses incurred manufacturing the components in the Grove City College machine shop. So it is important to note that real-world costs will be above that because we had access to some of those free things that help keep our costs low. So on this next slide, we're going to look at a Pareto graph and a sensitivity graph. These kind of show the breakdown of our spending to the 10 major spending categories. One glaring observation from this slide that you can notice is that the sleeve and the collar accounted for around 64% of our spending. And this is because the sleeve and the collar were the two outsourced components of this project that we had outsourced and produced for us by Brilics Industries. These were outsourced due to their large size, their critical tight tolerancing, as well as their demanding heat treating that needed for those components. Beyond those two components, the remaining 8 all were under 10% of the total spending. And that was because for all those parts we were able to manufacture in-house, as well as they're much simpler and didn't require as much tolerancing. So next, we're going to move on to kind of review some of the design requirements that Nick shared with us. We're going to kind of reflect to see how this project meets those, if we're confident in the results that we have without testing. And so our first two critical to quality requirements of successfully recovering 80% of gears, as well as if we're under the maximum half-an-hour touch time requirement, we're currently unsure if we meet those requirements because we were unable to actually take our apparatus to Wabtec and try to remove gears. Additionally, we are confident in some of our soft requirements that we will exceed those. First, with able to be using the apparatus on a broken crankshaft, we're very confident that we're able to do so because we designed all of our components into what we identified as a critical radius. That meant those components can be assembled without touching the ground if a broken crankshaft was sitting on the ground because it couldn't be mounted to engine stands. Additionally, we're currently unsure if we would be able to remove the gear without damaging the crank. And again, that's due to our lack of testing. We wish we were able to test the apparatus and see if we would be damaging, but at this time we're unsure. However, we are confident that we don't need an additional hydraulic pump to use our project. And that's because of that custom hose assembly that Mac talked about earlier. And finally, we're very confident the total replacement cost for our apparatus would be under $10,000. And this is because we outsourced our two major components and still came well under our budget. And even though we had some beneficial free labor as well as help in the machine shop, if Wabtec had to do this project over again, we're very confident that with the extra amount of budget that we did not spend, they would be able to outsource those as well and come out with an apparatus under $10,000. In conclusion, we first want to give some special thanks to some many people that were very helpful in this project. We first want to thank Justin Fowler because he was our day-to-day contact at Wabtec, and without him, none of this project would be possible. Additionally, he's a Grove City College alumni, and we know he was instrumental in getting this project started. So we want to thank him for giving this opportunity. Additionally, we want to thank Jack Dowell and the rest of Wabtec Corporation, as we met with Jack on a constant basis because he was the PE for this project, as well as we met with a group of other Wabtec engineers that helped keep this project on track and make sure we were meeting Wabtec standards. Additionally, we want to thank Jen Page for his help in the machine shop, as he was instrumental in helping us make both the backing plate and the clamps. We want to thank Stephanie Adams for help in purchasing and making sure that we were spending our money according to the school's standards, and as well as getting our source components on a timely manner. Additionally, we want to thank Thomas Benyo and Brilics Industries Incorporation for helping us source both our collar and our sleeve. And finally, we want to thank Dr. Ulrich for his help in this project as our advisor and helping us on a day-to-day basis in our meetings and making sure our project was going as scheduled. So overall, we want to thank all of you for listening to our presentation, and we want to welcome the floor open to any questions you guys may have.
Okay, thank you very much. We'll now open the floor to questions. Again, please indicate in the chat you have questions, or just go ahead and activate your microphone if you joined in through a browser.
Hey guys, this is Brian Montgomery. When you guys were working on this project, which my former employer, we made many fixtures for GE, what was one of your biggest safety concerns with using this?
Thank you for your question. Our biggest safety concern was the intense hydraulic pressure that we had to deal with. It takes just under 9,000 pounds of pressure to float the gear usually. So we just sort of rounded it up and said 10,000 PSI. So dealing with that hydraulic hydraulic fluid and that much pressure that it's under. That was critical for not only sealing the fluid so that it wouldn't, go everywhere and create a hazardous environment, but also we had to be very careful with our hydraulic seals, our O-rings. We spent a lot of time doing calculations. Alex can talk about that. He was a genius when it came to O-rings. And also just, making sure that we choose steels that have a high enough yield strength. It took some extra heat treating. So that just took anytime you're dealing with, hydraulic pressures that high, you just want to make sure that, all your numbers were right and that you incorporated enough factor of safety so that there was no harm to a laborer possible. I don't know if Alex, you want to say anything more about that?
Yeah, definitely the hydraulic pressure was our main concern because we wanted to make sure that first we wouldn't leak because even though the hydraulic fluid's not compressible, so it's not going to explode in a manner that'd be dangerous, but like we didn't want to have a geyser in the work environment, as well as we needed to make sure that if we did break a seal, that it was all going to fail safely. And so I know Sam worked in a lot of spent a lot of time designing these vents on the sleeve so that if a seal did break, we would actually like calmly leak pressure rather than spring a geyser. And additionally, we need to make sure that we tested a FEA case on most of our components of that seal failure instance to make sure like the sleeve wouldn't fail due to buckling, some other things. And finally, on the backing plate, there's some tabs that extend to actually catch the gear because we're currently unsure since we haven't tested this. There's a very good chance that as soon as we apply that hydraulic pressure, the axial force that still exists between the components up into the O-ring still might be enough to shoot this thing off the shaft. So basically, we just have to be prepared for every single case because we just didn't know how it's going to react. And so it took a lot of, for me, effort to get it to where it's at. But we're really confident it's a safe apparatus.
Any further follow-up to that question?
No, that's good. That's good. That's definitely things to consider with the pressure and also with just worker wear and tear in that environment. So thanks, guys.
Thank you for that question. Dr. Allison had a question.
Yeah, just a quick question. Once you slide the gear and the collar onto the sleeve, and let's say you remove those three components, put them bring them over to a workstation, how do you get the gear and the collar off of the sleeve? Is it a pretty tight press fit once you release all that pressure, or and can you just press that out? Just wondering what you would do there.
Yeah, so the collar is press fit onto the sleeve, and then the gear is press fit onto the crankshaft. So it sounds like a goofy design, but there is some clearance between the sleeve and the gear whenever that hydraulic pressure is taken off. So yeah, so as long as through cycles and through fatigue, the sleeve doesn't warp, there should be just enough clearance, and then that added hydraulic fluid that exists in there will help to slide the gear off. But the collar stays press fit onto the sleeve for the life of the tool. If that answers your question. Sam did a lot of work with the sleeve. He can chime in there too.
No, that sounds good. Thank you for that answer.
Okay, thank you for the question. Any further questions from anybody?
Hello, can you hear me?
Yes, Jack. Hi.
Yes. Hi. Yeah, this is Jack Dowell from Wabtec, and it's more of a comment than a question. I would like to thank the team for all of their hard work. They did a very professional job in tackling this project. I think they've come up with a very innovative design, and I'm confident that it'll work in practice because of all the details that the team has worked through. And I'm really looking forward to doing the trials with the hardware that they've made. at our shop here in Grove City. Hopefully sometime this summer, once our workshop is back on regular type of work duty. But again, thank you very much, team. You did a great job. Good presentation too. Thanks.
Thank you, Jack. Thank you.
Any other questions or comments?
I have a question. This is Mrs. Henley here.
Go ahead.
So I noticed your guys' clamp design, and I've actually seen the actual clamps, you know, in the machine shop. Were those specifically over designed? Because they seem pretty beefy for their size.
Yeah. Jake did a lot of work on the clamps. He did a really good job. Yeah, I'll let Jake answer that. But it has to do with a lot of the hydraulic pressure. So Jake, go ahead.
Yeah, so those are actually not significantly over designed. There are a few areas that are slightly beefier than they need to be, but to be able to machine it easily, as well as keep the stresses down in some of those sharper corners, everything is sized as about as large as it can be, or as small as it can be, I should say.
Any further follow-up on that question?
Good job, guys.
Great, thank
I'd
you.
like to add my 2 cents worth. Nice, well done, guys. Great project.
And this is Justin Fowler. You guys able to hear me?
Yeah, Justin.
Hey, I just want to second what Jack said too here. I mean, to be quite honest, there's a lot of adversity. I mean, I don't want to just say it just for your guys' team, because there's a lot of teams involved in this that have unique set of circumstances, a lot of stuff going on in the world today, and it just the fact that you guys were able to go through and kind of finish up with this, along with a lot of schoolwork and all of just the things you have to deal with day to day. It's impressive. I mean, grow from it, learn from it. You guys had some unique opportunities going through our design process and working through some of the stuff that we have to do day in and day out. So take that and just kind of use that as an opportunity when you guys go throughout your career. And just if you guys have any questions, feel free to reach out. We'll be able to update you whatever we can go forward too.
Thank you, Justin.
Great. One last call. Any more questions? Any more comments?
I would like to make one more comment, and I don't think they really hit on this very much, but this team actually has literally built all of the, they've outsourced a few parts, but the parts for this thing are done. They are in the shop and in the lab, and the only thing that's missing is the opportunity to meet together as a group at Wabtec and try it.
Great, thank you for that, Dr. Ulrich. Any other comments? Any other questions? Great, wonderful job, guys. This concludes our presentations for tonight. Thank you all for coming, and also thank you to the sponsors and to all the faculty that have been involved. All of you did a wonderful job, and just thanks again. We will see you again tomorrow. Tomorrow at 5:45, we will open up the channel for people to join, and we will start tomorrow's presentations at 6 o'clock. Thank you very much. Have a good evening.
Thank you.